All right. Back to the standing waves categories. Standing waves can broadly be classified into two types: transverse standing waves, longitudinal standing waves. Now, how to identify in the exam which one is the transverse, which one is the longitudinal? If in the exams you are given a string, so what's this? This is a particular string which is connected to an object over here. And then we have an oscillator on the left hand side. So roughly just remember in the exam, if you have been given a string, that is a transverse standing wave. On the other hand, if you have two kinds of pipes, so any pipe question will be longitudinal. Pipes are of two types: pipe open at one end, closed at the other end, or which is a pipe open at both the ends. Now we'll analyze the exam formulas which you are supposed to know. Let's start with the transverse standing wave. As I explained earlier, we have basically an oscillator. This is the device which will oscillate the left end of the string. So this particular string is connected with an object. Over here, you can see there is an object hung from the string. The role of this object is basically just to produce tension in this string, which means just to keep the string tight. Then what's going to happen when the device oscillates up and down? So it is going to produce a wave pulse, like we analyzed in that 2% string standing wave. So the wave will start to move towards the right hand side, and when it hits the rightmost end, so this is a fixed end, and what happens when a wave hits a fixed end? It will reflect, but it will invert. So it will invert and then it will go back. Now what's going to happen? The device is oscillating continuously. So wave, basically a wave train will be produced going from left to right, and then continuous reflection will also happening from this fixed end. So the regular wave train and the reflected wave train will superimpose, will interfere to produce a standing wave. Let's see how does it look like. Have a look at this animation. Carefully observe the standing wave. You can see this is a standing wave, smallest. There is only one loop, which you can see the points are just going up and down. Only one loop because you have only one antinode right in the middle. Now in the exams, this sort of a oscillation, of course, animations is not possible to be seen. So in the exams or the questions, you will be shown diagrams like this. This is the animation of the smallest standing wave possible, one loop. Now, how to solve questions? Because that's the whole point of this. Analyze this particular end on the left hand. It's a node. Similarly, the rightmost end is also a node. We have written n is equal to 1 here because we have one loop. So don't get confused with n and node. Node and n are different. N is the number of loops. Now, remember what was the distance between two consecutive nodes? That was lambda by 2. And this is also equal to the length of the string. So basically, we have one particular string which is connected between the device and between this fixed end. That length is equal to lambda by 2. So if I equate L with lambda by 2, we will get lambda is equal to 2L. Now, we have to find the frequency. So we use the basic formula. Speed of any wave is given by the product of frequency and wavelength, which means frequency is given by V upon lambda. And since lambda was 2L, in this case, we will write frequency as V upon 2L. Hence, see, this was the smallest possible standing wave, which had only one loop. And that's why the frequency which we get, V by 2L, this is called the fundamental frequency in this case. Moving ahead. Same animation, same setup. The only difference is the device will be oscillating with different frequencies. You can see here, first scenario, frequency will be 15 Hertz. Second scenario, 30 Hertz. Then third scenario, the frequency has been tripled. let's analyze. So the 15 hertz is going to produce only one loop. 30 will produce double, which means two loops. 45 will produce three loops. Let's have a look at this animation. Now this animation has been divided into two parts. The first half of the video has been shot with a high-speed camera, so you will see a slow motion effect. And the second half of the video is like with a regular camera, which means you will be able to see as if you are looking at it with your own eyes in a lab. Observe carefully. So this is all super slow motion. You can see standing waves. Points are basically going up and down. In a few time, you will be see the actual effect. Okay, have a look. This is what we will see when we look at it with our own eyes, because our eyes are not fast enough to get that kind of a slow motion effect. Now observe, the first wave is having one loop. You double the frequency, you will have two loops. You triple the frequency, 15 into 3 is 45. That will triple the number of loops, three loops. Now in the exams, the same setup is described like this. First harmonic, one loops, we call that as fundamental mode. Second harmonic, two loops. Third harmonic, three loops. That's it. Now, back to the main formula, which we have to use to solve all the questions. As we just discussed, in the first harmonic fundamental mode, we already did that derivation. So frequency was V upon 2L, where V is the speed of the wave. Let's say this is F1, fundamental or the first harmonic frequency. In the second harmonic, let's derive the same expression. So we will employ the same logic. Velocity is frequency into wavelength. Frequency is just V upon lambda. So all you need to do is figure out what is lambda in this particular situation. Now, we have a node at the extreme left. You have a node at the extreme right, but the point in the middle, this is also a node. Now, as we just discussed, the distance between any two consecutive nodes is lambda by 2. So lambda by 2 here and lambda by 2 here. So the total distance will be lambda, which we can equate with the entire length of the string. So length of the string will be equal to lambda. Now, since L and lambda are equal, we can use the frequency formula. It will become V upon L. So let me write the second harmonic frequency is V upon L. Similarly, in case of third harmonic, let's do the same derivation. We'll have 1, 2, 3, 4 nodes, which means the distance between any two nodes is lambda by 2. We already know that concept. And that will be equated with the entire length of the string. So in this case, length will be 3 lambda by 2. And if you make lambda as the subject, we'll get 2L by 3, which means if I now find out the F3, the third harmonic frequency, which is V upon lambda, it will come out as V upon 2L by 3, which simplifies to 3 times V by 2L. This is the third harmonic frequency. Now let's analyze F1, F2, F3. F1 was V by 2L, F2 was V by L. Now V by L I can write as 2 times V by 2L, which is basically double the original frequency. So let me write 2 times F1. So F2 will be 2 times F1. Similarly, if you focus on F3, F3 is 3 times V by 2L. So F3 will be 3 times F1. Now analyze the pattern between F1, F2, and F3. Basically, the F1 is just getting multiplied by integers, various integers. So 1, 2, and 3. Now, if you combine all of this, we can create a generalized formula. And the formula goes like this. In a transverse standing wave, frequency of n, this is called the nth harmonic. Frequency of the nth harmonic will be n into V by 2L, where n is any positive integer, V is the speed of the wave, L is the length of the string, and n is the number of harmonics. So first harmonic, one loop. second harmonic 2 loops, third harmonic 3 loops. That is what the N basically represents. And in the exams, you should also remember the formula of V. How do we find the speed formula? So the speed formula is this. Speed of a wave in any string is given by square root of T by mu, where T is the tension in the string. Mu is the mass per unit length of the string, which means I can write mu is total mass of the string divided by the total length. That is what we call as the speed. All right, let's solve a question based on this. We have, so the mass per unit length of a guitar string is given. So basically the value of mu is given. The T is given as 40. So part A is find the velocity of the wave. So you just employ the formula T upon mu. So we get square root of 40 by 1.2 into 10 to the power minus 3. And now if I solve this, let me see what do I get. Just a sec. Okay, so I'm getting 182.57 meters per second. This is the speed of the wave. Now let's read the B part. Calculate the frequency of the first harmonic if the vibrating length of the guitar string is 63.5. All you need to do is just remember the basic formula in case of a transverse standing wave. Frequency Fn is Nv by 2L. Since in this question we are dealing with the first harmonic, so N will be 1. Speed we already have found. So F1 fundamental frequency will be 1 into 182.57 divided by 2 times length. Don't forget to change the length into meters, 0.635 meters. Now, if I solve this, let's see, what do I get? I'm getting F1 as 143.75 hertz. And that is the answer to this question. Now, the next question you have to solve on your own. That's a homework question. It had 2 parts. Part A is this, and part B is this. Solve this as a homework.